In this highlight video, we will learn how to predict acid-base reactions. We will build upon what we learned about acid and base strengths, and we will use that information to learn how to write out acid-base reactions, how to predict products, and once we've done that, we will learn how to predict the direction of the equilibrium, whether the equilibrium lies towards the products or whether it lies towards the reactants. Our first step will be to compare the two reactants. Of these, the stronger acid will act as the proton donor, or will act as the acid. The weaker acid is going to act as the base. Let's look at two examples. In the first example, we have the reaction between acetic acid and water. All right, so we need to know something about the pKa values, or the acid strengths, for these two molecules. All right, if we go to our general table, we would find that the strength of carboxylic acids are usually around 5. Okay, acetic acid is just a little lower, is about 4.8. The pKa of water, you might remember this from Gen Chem, is 15.7. So which one of those is the stronger acid? All right, so acetic acid is the stronger acid, so it is going to be the proton donor. The way we can draw out these reactions is that there's going to be a non-bonding pair of electrons on the base, and those electrons are going to be used to form a bond with the proton. That proton leaves, so it breaks the hydrogen-oxygen bond, and so those electrons go back onto the oxygen. So there's the electrons from the hydrogen-oxygen bond, and we have formed hydronium ion over here. All right, so we have in this reaction, we have acetic acid acting as the acid. Water, what's it behaving as? So it's playing the role of the base. This is called acetate. It's the conjugate base of acetic acid. So this is the conjugate base. And we know that this is hydronium ion. And hydronium ion in this reaction is the conjugate acid. All right? So we compared the acidity of these two reactants. The stronger acid of those two is going to act as the acid. The other compound will act as the base. All right, in the next example, this is ammonium ion. And it reacts with water. Okay, we already talked about water has a pKa of 15.7. If we look back at our general table, our general ranges, we would find that ammonium ion has a pKa of around 10. All right, so of these two, ammonium ion is the stronger acid. So water will again act as the base. It will remove one of these protons to form ammonia, and there's the pair of electrons that was in the hydrogen-nitrogen bond, plus hydronium ion. All right, so we have ammonium ion, we have water, we have ammonia, and hydronium ion. Okay, we have our acid, we have our base, we have our conjugate base, and we have our conjugate acid. All right, let's do. In the top example, again, we have acetic acid, and it is shown to be reacting with hydronium ion. So in this case, it seems like we have two acids that are reacting with each other. So again, we have to compare the two. So the pKa of acetic acid, remember, was about 5. pKa of hydronium ion, remember, any of these compounds with an oxygen with a plus charge and a proton has a pKa of less than 0. Right, so hydronium ion is a stronger acid than acetic acid. So that's going to form acetic acid to act as a base. Right, so there are two ways that acetic acid could act as a base, because we have two oxygens, each of which has 2 pairs of non-bonding electrons. All right, so we could have these electrons up here removing a proton from hydronium ion. If we did that, let's draw out what we would get. We detach our hydrogen up here. We'd have a plus up on that oxygen. Okay, we'd get this. And if we tried it from the other oxygen, we would get this conjugate acid. Okay, so now what we have to decide, because we're starting with the same acid and the same base, it's going to be whichever of these two conjugate acids is more stable is going to be the one that forms. All right, so how do we tell which of those conjugate acids is more stable? All right, well, we want to look at the types of things that we've learned about stabilizing charges, right? So if we can spread out the charge, then that will make it more stable. So is there a way to spread out the charge on one of these compounds? All right, so actually there is. Look at the conjugate acid on the left in red. In this case, we have a pair of non-bonding electrons on an atom, on the oxygen, which is next to a pi bond. So in this case, remember, we can push those electrons toward the pi bond, and those electrons can go up on the oxygen. All right, so this species over here has resonance. What about the one on the right? Okay, it could, in theory, do the same thing, but that oxygen already has a plus charge on it, so the resonance contributor would have an oxygen with a 2 plus charge on it. And so this one is going to be not stable. So this is less stable. All right, so the red one here is going to be the one that's formed predominantly. So when we have carboxylic acids like this, if they're going to be protonated, they'll protonate up on the oxygen that's part of the carbon-oxygen double bond. Let's look at the next one. So here, this is called an amine. All right, we could just classify it together with ammonia that we saw on the last slide. And this is hydronium ion. Okay, hydronium ion we know is very acidic, has a pK of less than 0. And amine, if we look back to our tables and we look at the pKa of ammonia, which is this, all right, NH3, those NH bonds will have a similar pKa. And so this has a pKa more about 38. All right, so hydronium ion is much more acidic than the amine. So the amine, with its non-bonding pair of electrons, will behave as the base, and it will remove a proton from hydronium ion. So the nitrogen now has 3 hydrogens. So when nitrogen has 4 bonds, remember that it has a plus charge. We'll have plus water. All right, so this is an ammonium ion. All right, we got 2 more here. We have an alcohol, has a pKa, well, of about 16. Hydronium ion has a pKa of less than 0. So again, hydronium ion will be the acid. The alcohol has to be the base. Go like this. We will form this oxygen here. Let's draw all the non-bonding electrons. So this is called an alkoxide as a general name, plus water. All right, the last one also, here, so this is an alcohol. The last one also is a reaction of alcohol, but this time it's reacting with a base, hydroxide. Okay, so the alcohol still has a pKa of around 16. The pKa of hydroxide, because if it gave off another proton, it would give us O2-, which is very unstable. I don't know exactly the pKa of that, but it's going to be very high. All right, so the alcohol is actually more acidic in this case. So hydroxide is going to remove the OH from the alcohol. This is going to generate a new alkoxide, just like up above, plus water. All right, so this is how we predict, or this is how we write out acid-base reactions. If we start with an acid and a base, we can predict what the conjugate acid and the conjugate base will be. The second step in this process is going to be to determine which direction the equilibrium lies, if it lies towards the products or lies toward the reactant, or if it's halfway in between. So the way that we do this is we compare the acid and the conjugate acid. So we compare the acid from each side of the equation. And the equilibrium will lie away from the side of the stronger acid. So the stronger acid pushes it away to the other direction. All right, so here's all of the reactions that we already figured out with the products that we drew in before. So now what we're going to do, though, is we're going to compare the pKa of the acid on the left. So hydronium ion is the acid on the left. We said it had a pK of less than 0. The protonated acetic acid on the right has a pK of less than 0 as well. So from our kind of ballpark estimate here, we would essentially just get a mix of products and reactants. So the equilibrium would lie somewhere in the middle. We could probably dig out and find these pKa values in more detail, but we'll just go from our general ballparks right now. All right, so let's look at the next one. All right, the acid on the left is also hydronium ion, so pKa less than 0. ammonium ion on the right, pKa of around 10. So remember, the equilibrium lies away from the stronger acid. So hydronium ion is a stronger acid, so the equilibrium will lie in this direction. All right, the next one has an alcohol and hydronium ion. The hydronium ion seems to be our acid of choice here. We have this oxonium ion. It looks a little bit like hydronium ion on the right. All we've done is replace a hydrogen on hydronium ion with this carbon group. So these pKa's are going to be similar. So again, we'd have a mix here. This is our acid is around 16 for the alcohol. The acid on the right is water, 15.7, so it might lie just a little bit back to the left, but it would likely have a mixture as well here. All right, so this is how we determine the position of the equilibrium. We ended up with a lot of mixtures here, but what we look for is the stronger acid, and the reaction will lie to the opposite side of the equation from the strong acid. So go ahead and try these two examples on your own.